Welcome. Today I'm going to talk to you about the answers to the Introducing Work Kinetic Energy Theorem document here. Here we are on the first slide. You may remember from the initial unit that we had in this class that when objects are in free fall, free fall, right? You may remember has a special meaning, right? And that during free fall, which Bronco Brown is in, for all of this time right there, free fall means that the speed of the object increases by 9.81 meters per second for every second that you fall. And so the velocities here are very easy to calculate. You've got 9.81, and I'm going to choose, so you know, I'm going to choose downward as positive just because I can, and because it makes sense to me to go ahead and do that, because I know that I'm going to be going ahead and doing most of my motion in the downward direction. So it makes the most sense that I'm going to go ahead and have that. After 2 seconds then, he's got 9.81 plus 9.81, so that's a total of 19.62. And I think we got 3 sig figs on this, yeah, so let's just assume 3 sig figs on that. And then he falls for a third second, so we have to add another 9.81 to that, and so we get 29.43. Boom, like so. Excellent. Now, the momentum, remember, is just the mass times the velocity, so we're just going to go 100 times that, 100 times this. Let's see, 962, there we go. And 2943 with the sig fig bar above the 4 right there. Now, something weird happens between here and there, and that's that he experiences an upward force now all of a sudden, and so he's not in free fall any longer. So this is not free fall, and so you can't continue to accelerate in the same way because you have now a force that's trying to stop you. And that makes sense, right? You don't want to partake in a sport that you know is going to end up with you splatting on the ground. So hopefully that makes sense. So what that means is that the upward force then is applied and applied and applied until finally right here at the lowest point, you better hope that his velocity is 0, which means his momentum has to be 0 as well. Now, for him to go from a velocity of 29.43 down to 0, his delta V must be negative 29.43, right? You must agree with that because he went from 29.43 meters per second down to 0. So that's his change. His mass is still 100 kilograms. And the time that it takes him to make that change is still from 3 seconds to 5 seconds. So that's a difference of 2 seconds. And so what's the force? Well, thankfully we have Newton's second law rewritten here, so that we can go ahead and use that. And so the force is equal to the mass times the delta V over the delta T. So if I do that out there, I end up with, let's see, 29.43 times 100 divided by 2, and I get 1,471.5. And so if I do the math, I get negative, because it's against the motion, right? It's upward of 1,470 to the correct sig figs, newtons. There we go. And so that is what goes in right there. Hopefully that makes sense. Okay, on to the next slide. Okay, here we are at slide 2. And you may want to transfer over all of the information that you had from the first slide. So this was 9.81, this was 19.62, and this was 29.43, and this was 0. Okay. Now remember that this is in free fall right here. So you've got free fall going right there. So it's different than the bottom case where the same rules do not apply. And so if I want to figure out the displacement, how far something has fallen, remember that there was a specific formula that we developed to try to tackle problems like this. How far do you move when an object is accelerated? And that is the master motion formula, which we said looks like this. And so if you take a look at it here, All right, sorry about that. So the master motion formula is the one that you want to use for this, which I've written out right here. And in this case, you have to remember that the initial velocity, as it says right here, is 0. So this term goes away. So we're left with this. Now this, delta x, is just any generic displacement. So in our case, we're using a vertical displacement, so we're going to convert it into a delta y. You could put an h or a d or whatever makes you happy. Equals 1/2, and then the acceleration that the object experiences, of course, is little g, and then delta t is delta t, and then that has to be squared. And so we can figure this out fairly quickly by going ahead and plugging in those numbers. And so we end up with 1/2 times 9.81 times 1 squared equals, there we go, 4.905. So here we have 4.91 meters. And then we do the same thing, 0.5 times 9.81 times 2 squared. Gives us 19.62. And if you remember from Galileo, Galileo told us that the relationship between the distance something travels and the time that it takes to travel when it's being accelerated is a squared relationship, and that's why we use this formula. And then down here we go 44.1 meters. Now from here to here we experience a force, and that force is something we figured out on the last slide. If you recall, it was 1471.5, I think, newtons. And so we can go ahead and calculate that out, and we can use this formula right here, which is why I put it up there. This we want to make into a delta y, but otherwise everything else should be exactly the same. And so if I solve it for delta y, I end up with this. Delta y equals 1/2 m delta v squared over f. So this is 1/2 times 100 times the change in the velocity squared, so 29.43 squared, all over 1471.5, which I think was correct. So I'm going to go ahead and do that here. 1/2 times 100 times 29.43 squared divided by 1471.5 gives me 29.43. So 29.43, and it just so happens that it's the same. This and this number, it's just a random occurrence there. So from here to there is 29.43. From here to here is 44.1. And so what do I get when I add those two together? 44.1 plus 29.43 gives me 70.3.5 meters. Is that correct? Let's make sure, because it's early and my brain is not so great. 75. There we go. Good. Okay. So there's our answer for this last one here. So this actually goes, this is our answer that goes in right there. So hopefully that makes sense to you. All right, on to the next slide. Okay, so here we are on slide 3, and this should be pretty easy to figure out at this point. How much work did he have to do to lift himself up? Well, we know now how high he went, right? So his displacement upward is 73.5 meters. And we know how much he weighs, which is how much he has to lift himself up, because we can take his mass and multiply it by 9.81. And so we end up with a weight of 981 newtons. And so all we do is multiply those two together to be able to get it. Times 981 gives me 72,132.93 joules to 3 sig figs. So the work he does is equal to 72,100 joules. There we go. Where did that work go into after he stopped climbing? That's potential energy, which we go ahead and symbolize with a capital U. Work was done as he fell, but what did the work? That was the Earth, right? The Earth applied a force to him and caused him to change his position. In total, how much work was done as he fell? Well, the amount of work that he had to do to be able to lift himself up is got to be equal to the amount of work that the Earth did to pull him back down again. Okay. How much work did the bungee cord do on Bronco? Well, so we have the force right here. The force was 1,471.5 newtons, and it was applied over a distance of 29.43 meters. So we can figure that out just by multiplying those two together. And so the work, 1471.5 times 29.43 equals 43,306 joules. So 43,300 joules right there. What was the impulse applied to Bronco in the first 3 seconds? So the impulse is the force times the time. So his force was the force of gravity, right? So that equals 981 newtons. And it is multiplied by the amount of time that it took, which was 3 seconds. And so 981 times 3 seconds gives us a total of 2,943. There we go. Whew, man, having a rough time of it this morning. Now be careful when you see that J and that J. Don't forget that they are totally different. This is joules and this is impulse here. So that impulse is 2,940. And remember, impulse is in newtons times seconds. And so what was the impulse at the last 2 seconds? Well, that's the force that was being applied by the bungee cord. So that's 1471.5 newtons. And the time was 2 seconds. And so the impulse was 2,000, I'm just going to do this in my head, 2,540 newton seconds. Is that correct? Yes, that looks right. 2,940. Whoosh. Man, having a rough time of it. Let's make this. Let's do this. 2,940 newton seconds. There we go. Much better. Okay, on to the next slide. Okay, we're almost done. So the work done by the Earth becomes a certain amount of kinetic energy. So remember that formula that we had way back on the second slide is that the work is equal to the change in the kinetic energy in this case. And so the work done by the Earth is the amount of force applied to Bronco Brown. Yes, Bronco Brown. And then that'll be the same as the kinetic energy. So what you're going to see is these two things are the same, as long as we're talking about the change in the kinetic energy being from 0 to the new number. And so the work is, one way to figure it out, that's just the gravitational force being applied to Bronco Brown times the distance that he falls. And so that's one way to do it, like I said. You don't have to do it this way, but what I figured out, it's a little bit easier, I think. But anyway, here it is. So here's what I got. I got these two should both be 4,860 joules, and then let's see, 19 times 9.8 gives me 19,000 with the bar above this, that 0 there, joules. And then last one gives me 8,900. Again, that's the same for both, right? Both of these answers are going to be the same. The amount of work done by the Earth to speed up the guy who's falling here becomes kinetic energy. So we can use that to try to figure out how fast he's going if we wanted to. Now at the end, his kinetic energy is 0, even though the Earth has done more work to try to pull him down. And so something must also have happened here. And so this work is kind of a question. We're going to talk about this particular answer this week. But something happens to cause his kinetic energy to go from that to this. And of course, you can start to see that it's the amount of force that's being applied up by the bungee cord. And that bungee cord is what's causing the change in the kinetic energy here. And so it's decreasing it. It's negative work by the bungee cord. So hopefully that makes sense. And it's overcoming the force of gravity of the Earth. So just be careful with that. We're going to talk about that more this week. On to the last slide. All right, here we go. So which car has the greater acceleration? Obviously the one with less mass. Sorry. It's before school. It is what it is. So the one with the less mass is the, let's see, compact car, because it has less mass. Which car spends more time on the surface of the lot? Well, that must be the sedan, because the sedan takes longer. It doesn't go quite as fast, and so it doesn't launch itself off the cliff until after it is has moved the whole distance, which it takes longer to do because it's not going as fast. Which car is moving faster when it reaches the edge of the cliff? Well, the one that has the more acceleration, which is the compact car. Which car has the larger impulse imparted to it? Well, impulse is force times time, and so they both have the same amount of force, but the sedan gets it for a longer period of time. So the sedan is the correct answer. Which car has the greater momentum at the edge of the cliff? Now this one is actually a trick. So you have to be careful with it. Remember that momentum, the change in momentum is equal to the impulse. And so the one that has the larger impulse should be the one that has the greater change in momentum. And since they both have zero momentum at the beginning, the final momentum is going to be greater for the sedan. Which one has greater work applied to it? Well, work is actually force times distance. And so force, wouldn't you agree, if the forces are the same and the distances are the same, the work is the same. So it's the same for both. So therefore, they both have the same amount of kinetic energy that they've gained. So you can see kinetic energy and momentum are kind of different in a very important way. And so, yes, it does contradict your answer from earlier. So you have to be careful with confusing your momentum and your kinetic energy. Which car spends more time in the air? Well, if they both launch from the same height, they all both fall in the same amount of time, as we talked about back in Unit 2 with free fall. So it's the same. And then which car lands farthest horizontally? Well, whichever car is going faster as it launches itself off the cliff is going to be the one. And so if you remember, this one is the compact car. So there you go. All right, thanks for watching. If you have any questions, please let me know. Thank you.